Not the first one so far. It's a bit nerve-wracking third year, isn't it? When you come in, it's a bit more serious, isn't it? Okay. I suppose everyone's coming in who's going to come in. Hello, my name is Hugh Owen. I'm obviously the module tutor for this course. This course is PHYS30141, electromagnetic radiation. As you can probably see on the boards up there. Now, if you look at those boards, are you happy to have them both displayed? Is that convenient or distracting? Does it matter much? Okay. I will occasionally show things on different boards. I have a set of notes I can put up as well. Actually, this lecture is an unusual one. It's the only one which will be on PowerPoint like this. The rest will be a kind of traditional handwritten course, which I'm sure you're all used to. I'm going to try to pizzazz it up a bit. Okay. The material at first appears dry, but I'm going to try to make it less dry. Okay. So it's a 22 lecture course, probably, roughly. I'm going to go at a fair pace, but I'm going to give you lots of help to get through it rapidly, okay? Third years, there's a reasonable amount of material, okay? So the first thing to say, oh, by the way, can you hear me okay? I shout quite loud, okay? If you can't hear me or you can't see what I'm writing, just like everybody else, shout out and I'll do my best to make things clearer. If any of you have any particular requirements in terms of audiovisual, audio or other notes and things, just to make you aware that all the course notes are going online. I'm going to put them up. There are 6 sections of the course and they go up in sections, and I'm going to give you full written notes, okay, which I think some other module tutors do as well, okay, and I will also be doing handwritten notes, and they should reflect one-to-one, okay. Now, has anyone found any notes from previous years online? Have they been circulated at all? I'm aware that sometimes happens, okay. They should be largely the same as last year, apart from section 6, which is coming later, which is going to be about cyclotron and synchrotron radiation, okay. So I'm going to try and help you orient yourselves on what to expect for this course as a whole, okay? Now, obviously, there are 2 similar sounding courses. There's electrodynamics, which some people think is the sort of cooler course. I'm going to try and convince you that this is the cooler course, obviously, okay? Terry White is doing a great course. His is focused on more theoretical things. This is a practical course. What I mean by that is I've worked extensively in electromagnetic radiation, and because of that, there's going to be lots and lots of numerical calculations. Okay, so if you are not familiar with your calculator by now, what's the correct brand of calculator to use? Casio. Correct, good answer. Okay, we'll be doing lots of numerical calculations, and that is to sort of give you a clue that there will be similar sort of calculations required in the examination. Now, there are 5 formal example sheets that will be coming out. I haven't quite decided. I'm going to put in a numerical refresher about halfway through. I may or may not put that into the main example sheet, but I will be distributing something to say, like a refresher to say, can you practice doing some of these numerical solutions. The reason I say that, and there's 2 things I want to get across right at the beginning, this is the 4th year I have taught this course. In the first 2 years, I had fairly high attendance, and the marks were also correspondingly high. Last year, the attendance was low and the marks went down. And the main area where people were struggling was in doing numerical calculations. I'm going to keep saying numerical, numerical, numerical. Okay? So make sure you're familiar and comfortable doing numerical calculations all the way through. Okay? Right. Now, obviously you've made it here, which is great. Is everyone in the room actually registered on this course for credit? Okay, there's some people doing it out of interest. Is anyone actually wondering which one to be going on, and they're trying to figure out which one they're doing? A couple of people. Okay. This lecture will not give you a good guide to what to expect in the rest of the course because it's on PowerPoint. Okay. Okay. So there's 2 lectures, Monday and Friday, reasonable time. So I hope to see you all there. All materials will go into Blackboard. That's all these notes, all the summaries, example sheets and answers will be let out as we go along. You're probably used to this. It's really a notes-based course. It's a classical physics course, so we do lots of paper stuff. And summary sheets will be made available to help you, but you should make your own. Okay. Now, I live in the Schuster Lab periodically, okay, because we have another institute, so I'm often off-site. You can regularly find me in the nuclear laboratory on the 2nd floor. You may have seen me there last year. I'm there on Fridays between 10 and 12 and 2 and 5. And you can obviously see that I'm not there between 12 and 1 because I will be lecturing here. Okay. So you can grab me around this if you have any particular issues. Okay. Right, now I'm going to skip over these things. These are all going to go online, but I'm going to skip through. This is the stuff you may or may not have already seen when you have looked at the module stuff online. Obviously, you've all read it in detail, haven't you? Yeah? Okay, we're going to be talking about the production, scattering and transmission of electromagnetic radiation or electromagnetic waves. Okay, so there is some detail there, but the most important thing is we're going to be talking about a fundamental fact about electromagnetic radiation, and it's how it is made. Okay, so I'm going to give you a little taster. We'll then get bogged down for a few lectures talking about the nature of electromagnetic radiation, and then we'll pop up again and talk about the generation in a bit more detail. Okay, but I'm hoping to try to inspire you. This is a really key part of physics. Right? We're going to have to talk about how the radiation is transmitted, reflected and refracted. You have covered some of this material before. Okay, so I'll go through that at a reasonable pace. But we'll also talk about the weird and wonderful world of cyclotron and synchrotron radiation, and the other weird bit, which is Cherenkov radiation. Okay, and that's the thing that's called Section 6, Sources of Electromagnetic Radiation. Okay, so that's the bit to expect. There'll be a little bit more of examination-wise at the end of the year. Okay. Now, examples classes. There are examples classes, and example sheets will be issued weeks 1, 3, 5, 7, 9. Okay, week 1 has already gone out. Have you seen it yet? Has it been distributed yet? No. Okay, it should be coming out shortly. I'll try. I'll issue answers a bit later on. Obviously, try and do them without the answers, obviously. And the workshop tutors are familiar with all this material, and they should be able to help you with any questions you have. Okay. This module is similar to previous year's courses, and as I said, it's the 4th year I've taught the course. And I have not radically changed the material from the previous lecturer, so if you're looking for clues about how the examination is structured and what kind of material goes in, the past paper should be a decent guide to that. Okay? And like I said at the bottom, experience of previous years indicates that attendance at lectures and examples classes correlates strongly with marks. Okay? I really want to get that across. Okay? So whilst I'm issuing the notes, I'm going to suggest it's a very good idea you turn up. Okay, to the lectures as well. Right, recommended text. Oh, by the way, I blabber on quite a lot. If you've got any questions, just stick your hand up, okay, or shout out. I'm not precious, okay. Just shout out, and I'll do my best to answer them. Okay. There are a number of course texts that you can look at. I quite like Bakafi, which is that dark one on the left. It looks quite mysterious, with that sort of black hole-like thing on it. I quite like that. Grant and Phillips isn't a bad book to refer back to. You'll have seen that one before. Electromagnetic Radiation by Frank Reed, bottom left, is pretty good. And Lorraine, quite a lot of example material has been drawn out of Lorraine Corson and Lorraine. That's another good one. And then there's a scary one at the bottom right. Okay, that's Jackson. Okay, not to try to offend anyone of a religious sentiment, but that's what we call the Bible of electromagnetic radiation. And as such, it's rather impenetrable and full of little incantations. So beware if you tread in there. But it's a great textbook. But you can look at it, but you don't have to look at it, right? It's those who are really keen on it, okay? But it's a very, very good textbook. It's regarded as the gold standard, but it can be impenetrable to start with, okay? So those are what I recommend. Oh, yeah, the one at the top right is not too bad either, okay? All right. I'm not trying to do it down, but I just happen not to mention that one. Okay, now there is a syllabus online, and I'm just going to briefly go over what's in the syllabus to give you a clue what's coming up. There won't be a one-to-one match of these exact lectures. I'm going to try to go a little faster on the stuff I suspect you already know. But as well as the textbooks, those notes I hope to go line by line through everything I'm going to cover in the lectures. Okay, and that should give you background material that we'll read in detail every little bit we go through. Okay, I'm also going to put up handwritten notes which should more or less reflect what we do in the lectures. Okay, if there is a conflict between them, it's the typed up ones which are correct. Those have been carefully looked at, I hope, to make sure we find out any typos. Okay, there are occasional typos, and if you find any, obviously tell me. Okay, so we're going to talk about the electromagnetic field, right? And we're going to talk about it a little bit more than was done last year. And we're going to talk in particular about the way in which electromagnetic energy and momentum gets transferred from one place to another in its basic form. And we're going to look at things like radiation pressure. Now remember, this is a classical physics course, right? By which I mean we don't try to invoke photons as quantum-like objects unless we really, really have to. So we're going to try to avoid those. Radiation pressure is one of those areas where we can't avoid it, right? We will then talk about sources of radiation, and the key thing here is sources of radiation. This is the key insight or the key fact about this entire course. In one manner of speaking, the generation of radiation, it can be thought of as being a single idea and one single equation. That's the Larmor formula, and we're going to look at its ramifications in a number of different ways, right? So I'm going to be reapplying that same idea again and again and again, okay? Hopefully not, so you get more in love with it rather than, obviously, I'm unhappy with it, okay? We'll then talk about radiation in matter and how plane waves will move, and there will be a particular aspect of that to do with plasmas, which I hope you find fascinating, and there are a lot of practical ramifications about how electromagnetic rays propagate through plasmas. And for example, we will find out why it is that gold is gold in colour and why copper is red. Okay? I want you to go away and have a think about how many metals are not silver in colour. I believe there are only 2. That's an interesting little fact. And we will talk about why that is. Okay? We will also talk about reflection, refraction and scattering. And we'll look at that in detail and remark upon how the electromagnetic equations that we have been discussing relate to important physical phenomena. One of the most important of those is Thomson scattering. And Thomson scattering, you'll see that scattering is radiation. It's a form of generation of radiation. We will see that later on. Okay? And many of the scattering phenomena that you have seen, like Rayleigh scattering that you've come across before, and other forms of scattering, including Compton scattering, are all the same thing. We will see how that works. Okay? And then we get on to my favourite bit, which is guided radiation and sources of radiation. And importantly, we will look at, this is section 5, we will look at what these things are. Now, ignore the gauge on the top, that's not the interesting thing. These things look like little metallic tubes, in fact that's what they are. And pass them around. You know, you're going to see these, they're little metallic tubes, just pass them around. Don't plunk them on the desk too much. Okay? First thing I'm going to ask you is, what are they for? Okay? And you look at them, they're metallic tubes, right? And they clearly have something to do with the transmission of electromagnetic radiation. But you're already aware, aren't you, that we transmit electrical signals, which are also can be considered to be a form of radiation transmission, through cables. So one thing to ask yourself is, why are we using these objects? When do we use them? And if you look at them, you notice they're rectangular. Why are they rectangular? Why are they made of metal? How is it that I can carry a signal when there's only one conducting surface on those things? It's made of copper, right? It's joined all the way round. Normally we think of signals as having one wire there and one wire there, right? You can have a voltage between them. How does it work with one of those objects? So that's what section 5 will give us insight into. And very importantly, why do we bother doing that when we could just do it in free space? Okay? So I'll leave that with you as an idea. Now, finally is my favourite bit, because it's what I've done professionally for a while, which is practical sources of radiation. Right? And practical sources of radiation are primarily, actually, synchrotron and bremsstrahlung radiation. Now, I'm going to start asking you questions. Where would you find a bremsstrahlung radiation source? Does anyone have ever come across one of those? Don't worry if you haven't, but has anyone ever heard of one, or where it might be used? Where would you use a bremsstrahlung source? Stunned silence. That's okay. It's the start of term, okay? Don't be shy later, okay? I'll come back to that, shall I? Synchrotron radiation. Have you heard of synchrotron radiation? Has anyone did like an astrophysical course where you covered synchrotron radiation? Yeah? Where was it described what it was? Ish, go on. Hazard a guess, don't worry.
I think so. I don't know how to explain it.
Go on, have a bash. What would you say?
It's like charged particles are slowed down or go around in a circle.
Ah, exactly. Okay, bremsstrahlung is the slowing down, okay, and synchrotron radiation is the motion in a circle. And that's actually, they're both the same thing. Okay, we will join those two concepts together, and the basic message here is that charges will only radiate radiation if they are accelerated. So it's an acceleration that causes radiation. That is the key fact of this entire course. Right? We will look at what that means a little bit later. Right. Okay, 15 minutes in. I have a pause. Any questions so far? Is there anything that isn't clear about how the course will be run. Cool. Have we got everyone in? 2, 4, 6? About 40ish, which is not too bad. Could be better, couldn't it? You should convince your friends to come along, okay? Right, some pictures to get you going. This, does anyone know what that is? Actually, it might even say on the slide. No, it doesn't say on the slide. Do you know what that is? I mean, it's a big building, and it's in Oxfordshire, okay? And it's got like the silvery building on the outside and some other building on the inside, right? And inside that building is a tube of metal, right? A vacuum tube. And inside that tube circulate electrons. And those electrons, as they go around and round inside that tube, and there's a tunnel inside that building, those electrons pass through magnets, right? You can see on the bottom left there, let's see, can you see this mouse okay? If I can move it around, there it is, see that mouse there? Okay, so this is a cartoon picture. This is a North Pole, say, and this is a South Pole, actually. That's the wrong way up, isn't it? The top one's a South Pole and the bottom one's a North Pole, right? So that's a South Pole there, and that's a North Pole there, and when the electrons pass through, they're bent to the left. You should confirm that for yourselves, okay, or using your cross-product rule. And because of that, there is an acceleration. And because of that acceleration, electromagnetic radiation is released by the electrons. All right? And it's called synchrotron radiation. It's called synchrotron radiation because the accelerated device within which the electrons are moving is called a synchrotron. Okay? So there's a simpler form of radiation called cyclotron radiation, and no prizes for guessing that it's called cyclotron radiation because the object in which it was discovered was called a cyclotron. So we will look at the differences between those two devices, because understanding those devices and the nature of the particles as they pass through gives an insight into the differences in the nature of the radiation. And the primary difference is that synchrotron radiation is for relativistically moving objects, which many subatomic particles will be, won't they, if they're of practical interest. And cyclotron radiation, they are not relativistically moving. Okay, so we'll come back to that a bit later. But that's the key difference in the nature of the acceleration. It gives radical differences in the way in how the radiation looks. Right? So these sources of radiation, synchrotron radiation sources, there are around 60 of them in the world. They cost hundreds of millions of pounds, and clearly people want the radiation that comes out of them because they're prepared to pay that amount of money. Okay? So this is why it's an interesting thing to look at. These are the brightest way you can generate X-rays. There's no other way of generating X-rays which is as bright as these devices, and that's why it's interesting to study this subject, I would say. Okay? There's a whole career, a whole technology, a whole industry basically located around this basic idea. And you can see there's these other devices here, right? See that? You don't just have to have one dipole magnet, you can have many of them, and they switch backwards and forwards. So rather than the electrons going through and being bent one way only, they'll bend left and right. Okay? They wiggle, so it's called a wiggler. All right? Or if it's more gentle, they're called undulators. So I'm telling you these words so you can look them up online, so should you wish, and you can find out a little bit about them, right? So modern science, modern education is all about the right Google search terms, isn't it? Right? So wigglers and undulators, look them up, and it will give you a clue to how they work. Right? Now a little bit more detail. That's what's going on inside. Okay? So you can see I have some dipole magnets. They are there, and that's where the electrons are being accelerated. So there's a little vacuum tube. Why do the electrons have to travel within a vacuum? Why can't we just send electrons through air and then so I have like a permanent magnet, right? I have a North Pole here, South Pole there. Actually, the other way up, right? This one, South Pole there, North Pole there. Electrons going that way, and they get bent that way. Why can't I do all this in air? Why doesn't it work? Take it, sorry?
It would collide with the atoms.
It would collide with the atoms in the air, okay? Simple answers are always the best ones, aren't they, right? So we have to evacuate the vacuum, we have to evacuate the space where the electrons are passing so that we don't undergo scattering. And actually, that passes through air. If it was a more solid target, like it could be like a tungsten target, a piece of metal, like a nice heavy metal, where I've got very large nuclei with a high charge in them, when the electrons pass through a lump of metal, it's not so much that they're causing the atoms to ionize, but they're experiencing forces from those nuclei, and those forces give a large acceleration, and that's bremsstrahlung. Okay, so those are the separation between those two concepts. Okay, so here's the inside. So here's inside that building. You can see, if you look closely, you can see there's the vacuum vessel. Can you see that? Looking down there, right? And there, oh, it's still the same colour, right? There's an actual green dipole. And you can just about see there's a north pole. If I look, there's a north pole there. Sorry, hang on, which way? And that's a south pole there. Yeah, south pole and a north pole. And you can see these brown things. Those are coils of copper wire, and you pass a current through them, and you can make the magnetic field. That's how it's done. That's how you make the magnetic field. Okay? And then the green things is painted steel that helps to guide the magnetic field through the vacuum vessel, and the electrons pass through it. Okay? The other red things and the yellow things, well, we'll come back to those. Those are other kinds of magnets. They don't have so much of a role. They're very important, but for the radiation, not so important. Okay? And here you see this is an undulator. Okay? So this is slightly different. There's no cores of wire in this one. Right? So if you look here, along the top, there's loads of little permanent magnet blocks. You know, like those things you can buy on eBay, little piece of permanent magnet, neodymium-ion boron. Okay? And you have them facing different ways up, so sometimes the field goes that way, and sometimes the field goes that way. Okay, up, down, okay? And you already, of course, you know that if the magnetic field is pointing up, then the particles bend to the left, and if the magnetic field points down, the electrons bend to the right. Okay? Always perpendicular, right? That's an important fact, isn't it? That the acceleration is always perpendicular to the direction of motion. Yeah? So magnetic forces, what do we know about magnetic forces acting on charges? That's different from the way an electric field acts on a charge. It doesn't do any work. Okay? So because the magnetic force is always perpendicular to the motion of a charge, no work is done, but somehow the acceleration is giving rise to that electron emanating photons. And those photons are carrying away energy, aren't they? Okay? Again, we'll fill that detail in later, but that's the basic idea. So the thing to start wondering about is, why is it that the magnetic field is not doing work on the charges? How is the energy, how's the energy balance being maintained between the magnetic field, the charge, and the photons being released? Okay, something to think about for later. Okay? So those are our magnetic poles, and here it is schematically, except things just being flipped 90 degrees now, and you can see those are the electrons. So because the magnetic field is now horizontal, the electrons are now going vertically up and down, and as they go up and down, they emit little bursts of photons every time they see a magnetic field. So that's one part. To me, that's the most interesting feature of this subject. Okay, but we have to reach our way into it to get there. Now, the reason I'm telling you all this is that hopefully it's of interest to you to know that each of the sections of the course all come together in these kind of devices. Right? So these devices are enormously important, and what you see here are not. This is to do with the guided radiation section, as well as the magnetic devices which are deflecting the particles and causing them to emit radiation. We also wish to put energy into the particles, and that can be done with these objects. Now we're not going to look at these devices in detail, but these devices, as you can see, look, there's a tube, right? If you look closely here, there is, if I get my mouse there we go, okay, there's a little tube that runs all the way through there. So that's actually a free hole that goes all the way through that object, right? So you can put particles through it, okay, if you wanted to. In that regard, it looks a little bit like these things. Anyone know what these things are that I've passed around? What are they? So let's look back at this object. So this object here, we're not going to look at objects as complicated as these, but this is a similar nature to the things we're going to study in detail. Okay, in these objects, okay, there are these little cavities, and they're called cavities. Okay, in fact, this is called a multi-cell cavity because there are several cells, and these cells ring like a bell. If you know, with a bell, you can ring the bell by mechanically hitting it, or you can excite it via oscillating air going in from one end. But like an organ pipe. Yeah, an organ pipe is a similar kind of thing. This is the equivalent with electromagnetic radiation. I can excite an oscillating electric field inside that, and if the particles pass through at the right times, they will see an accelerating voltage, and the particles will speed up. And these are the devices that allow particles to go from a standing start, from zero kinetic energy up to the kinetic energies we require. So this is a particle accelerator. Okay? So this cavity is in essence the same kind of thing we pass around here, except of course there are no cavities in the objects we're looking at. So we're going to look at not those cavities in detail, but look at these things underneath. So rather than having electromagnetic waves which are trapped, the devices we're going to look at are devices which guide waves from one place to the other. So they're called waveguides. Okay? So that's what that section will all be about. So that's the bit that's this bit here. Okay? And the reason we're going to look at waveguides is it tells us a great deal about the nature of energy transmission from one place to the other. Why does we do what we do? And we'll look at a few different situations. Okay? So you can see that object there at the bottom is the thing I've just passed around. Okay? And the smaller the object, the shorter the wavelength of the thing that goes down it. Clearly, that's one feature of these devices. Okay? And you can see on the bottom left, that's a bigger one, right? There's some Chinese guys at the Chinese Spallation Neutron Source, and clearly they must be using waveguide there, which has a larger wavelength. So one of the calculations you will be doing, and you might be surprised that you'll see this come up in exam papers, is making sure you can calculate the kind of wavelengths that can be supported in these waveguides. Okay, that's a classic calculation that we're going to be doing. Okay, and it's very, very useful when understanding how to transmit radiation from one place to the other, which of course is part of this course. Okay, right. So you have seen these things before, but I'm just going to brush over them. We're going to remind ourselves of Maxwell's equations. You have seen all these things before. Okay? In some of the textbooks you will come across, you should be aware now that there is a difference between SI and CGS units. Are you already aware of this? Yeah? So particularly some older versions of Jackson will be written in CGS units, and some older textbooks you may pick up. In those textbooks, the formulae as well will look different. The permeability of free space, that mu naught value here, will have a different value. Okay? So just be careful when you're looking through the textbooks to make sure that it's an SI textbook, otherwise you may find yourself becoming quite upset. Okay? We will be talking in the main in SI units in this course. Sometimes we will change, but not very often. Okay? And I will conventionally use these symbols, which you should all be familiar with. Things like the current density. Okay, and we'll be talking about both free and bound current densities, which you've been coming across before, in rhos and J's, and electric fields and magnetic fields given in these conventional units. Okay, now we will tend to look at those in that form. And just to remind you, now this is all online, and I will be going through it in detail again. You don't need to take particular notes right now, but remember this is just the intro lecture. Okay, we will also talk about Maxwell's equations as they arise in a medium, and again, what I encourage you to do is just to refresh yourselves, and there is a refresher sheet as well for some of the mathematical stuff. Have a look through that and work through that, just to get yourself back up to speed on the kind of material you'll be covering. Okay, so you obviously may have got a bit rusty over the summer. Okay, and you will remind yourselves, and this is an important point here. Okay, I will try as much as I can to separate the total permittivity epsilon from the relative and vacuum permittivities epsilon r and epsilon 0. And you will see here, okay, in this particular formula, that quite obviously in this formula, this little epsilon is meant to represent the relative permittivity. Okay? When you see textbooks, you will see these values being used interchangeably. I will try not to. If you get puzzled, just put your hand up. Which one do you mean? You are going to have to get used to the fact that people will switch between relative and total. Okay, I'll try to make it as clear as possible. Okay, and it should be fairly obvious from the context. The other thing to watch out for is permeability. Right now, absolute permeability is 4 pi times 10 to the minus 7. Okay, relative permeability can vary in different materials. However, in virtually all the situations we will look at, the relative permeability we will assume is 1. So therefore that mu will appear and disappear as time goes by. Okay? So be aware that that will happen and become comfortable with it, okay? And be happy dropping it when you need to. Okay? So you'll see that little mu appear and disappear during the lectures. Okay? So again, become comfortable with that. You will see that. All right? So you're obviously aware of all these things. Now if you cast your mind back even further, you will remember the Lorentz force. And the Lorentz force is the fundamental equation of the action of electric field on a charge, isn't it? Okay, and we've already touched upon that difference between the action of a magnetic field, which does no work. So you should remember that there is no energy transfer between a magnetic field and a charge, but with an electric field there is. Okay, so we'll go into that in detail when we talk about the energy balance between electric fields and the energy in a system of charges. Okay, and as well as talking about the Lorentz force acting on a single charge, we will be talking about acting on a charge distribution. So we will be seeing equations like this appearing where we calculate the total force acting on a total volume of charge. Okay? So that's just the refresher bits. Okay. Any questions so far? How far are we through? Oh, half an hour, perfect. Okay. Okay. Now, just give me a couple of minutes. I'll give you a little break for a minute while I turn this on. This looks different from last year. That's even working. That's new. It looks old, but it's new. That's funny. Okay. We're going to jump in and get started as we need to go on. And so as I said, I'm going to go through the notes which are already there, but I'm going to go through them in several different ways. When I think it's useful to go through them line by line, I will, but sometimes I'll skip over a few lines of the derivation because you will see that there are line by line things we can go through. I will try to pick up the most important points. Okay. Now let's see if I can transfer over. So these lectures should already be online by the way. These notes. Okay. Visualizer. Let's see if that comes up. See if I can actually get that to come up. Oh yes, I need to display it, don't I? Display. Okay. Can I see my pen? Ah, look there. It's working again. Great. Okay. Now, I think this pen is fairly visible, but we'll see how we go, okay? So shout out if I'm writing too small, if it's too thin. Okay. Okay, now, what should we talk about? We've done half an hour of preamble, and we're interested mostly in radiation, aren't we? That's what this course is all about. So why don't we just spend the first 30 minutes thinking about charges and fields. So this is not part of the notes per se, but this is to whet your appetite so that it will carry you through the more turgid bits, which we have to go through on the way to talking about the nature of radiation. Okay? So what shall I draw? What kind of objects are we going to talk about that radiate? Well, what is electromagnetic radiation composed of? We already know this. It's photons, but what are they? How would we describe that classically? You're all scratching your head. He's the lecturer, he's supposed to be telling us, isn't he? What I'm trying to get across is you already know this. I'm just going to try to remind you of these facts that you already know. Okay? Photons are composed of what, coupled together? Come on, don't be shy. I'll give you one of them, electric field. What's the other one? Magnetic field. Oh, come on. You have to get better than this. Okay, look. So we know that electromagnetic wave is composed of a coupled electric and magnetic field, don't we? And this is a very hand wavy to start with. We'll get into some mathematics later. So, therefore, what kind of object can they be that can generate electromagnetic radiation? There must be things that couple to the electric and magnetic fields. What sort of objects are those? In very general terms. They must be charged objects. Yeah? Must be. So only things which have charge can generate electromagnetic radiation. That's a statement we can maybe fairly confidently say. So I'm going to draw a little plus for a positive charge. Now, of course, later on we'll be realising that all the things we conveniently work with are negative, but we'll stick with positive for now. Okay? So we imagine this can be any positive charge, and it could be a large ball, completely covered with charge. And if I were to move it in an appropriate way, it will generate electromagnetic radiation, and those things exist. Okay? You can make large macroscopic objects. We tend to imagine charges as being singular point-like objects, like a proton or an electron or something like that. And very often we talk about protons, electrons, but you know, in the advertising, in the BBC way, other charges are available. Okay, we cannot, but we also, in practical terms, we think about collections of charges. So one thing we can think about is when we talk about an individual charge. So I just noticed that's at the top there. You can barely see it. There we go. Let's zoom out. Ah, that's better. Okay, there we are. Okay. We tend to think of collections of charges, and these charges can be very numerous. So one of the things we will talk about in our later calculations is bunches of charges. Okay? The objects that we use to generate radiation practically are very, very many electrons. And a good number to start to whet your appetite is imagine 1 nanocoulomb of charge, okay? Which is clearly much, much bigger than the charge on an individual proton or an electron. Your very first starter for 10 question is how many particles is it? How many let's say how many protons is that? Okay. So as a very first thing to do to start getting used to calculating total amounts of radiation and total amounts of stuff going on is to have an idea of how many particles are involved. Okay. Let's start with a single charge. So we have a single charge, and what do we know about the nature of a stationary charge? What does it have? How do we know it is charged? Well, you can tell me. If I'm gonna...
A uniform electric field.
It has a uniform electric field. Okay, so by convention, a positive charge exerts, emanates. You can use whatever words you like. It emanates an electric field. Okay, and remember, this is a stationary charge. And we should scratch our heads at this moment and remark stationary with respect to what? Because we already know there is no such thing as an absolute frame of reference, don't we? We are going to blithely pass over that in this course and not really worry about it too much. We may discuss it. Okay? One thing to be aware of in courses like this at third year and later on is we will give you calculations to do and things that will give rise to good practical answers, but there are holes here and there that will trap the unwary. Okay? So be aware that there are some conceptual holes here and there. I mean, this is a classical physics course, right? So we can do quite a lot by not invoking photons and not invoking quantum mechanics. And actually, for many careers, that's all you need to do. And you can do an awful lot that will tell you the nature of this stuff. Okay? And we can be quite happy with that. And remember that later on we can look at this stuff in a bit more detail by putting a quantum picture on top. But we don't need to do it yet. And there are things like the fact that that we have to worry about frames of reference. That again, we will dip into a little bit, as we're going to in a moment. But there are some other bits that we probably ought to worry about. But we won't worry about them now. Okay? Just be content with that. Okay? All right. So we have a stationary charge with respect to, say, me on this table. Okay? And it emanates an electric field. And we already are aware, aren't we, that we can draw what we call these field lines. They're not really there, are they? Okay? And of course, they're spherical. I mean, this is a 2D picture, isn't it? So they should be spherically symmetric. Here, they're just on a 2D sheet of paper, right? But we remark that they have the constant density as a function of orientation. If I have a chart sat on the table and I look at it from different directions, the number of field lines that subtend a particular area, right, like I put an aperture around, it should be the same, shouldn't it? Yes? Why is that? How could I turn that statement around? I can state it in another way, which is that charges don't have an orientation. Some kind of basic physical objects do have an orientation. Spin, things like that, right? A charge, in its classical sense, has no preferred orientation. We can't tell which way round it is. And that statement allows us to state that we have a spherically symmetric charge distribution, right? And we also know, don't we, that the number of field lines that emanate from that charge, not worrying just yet what a field line is, are proportional to the amount of charge we have. If we double the amount of charge, I double the number of field lines. Okay? And that statement is encapsulated in that idea that I can draw. So we will do this again in the next lectures just to get you going. Okay? I can draw a boundary, I can draw a surface around the charge, and I can count how many field lines I have. Right? And since I know that it's spherically symmetric, I can calculate the density of the field lines, And I remark that if I have a larger boundary, right, which is say twice the radius, then the density of field lines must fall by a factor of 4, mustn't it? Yeah? And that's Gauss's law, isn't it? And it's that statement that the number of field lines is proportional to the charge which gives rise to that statement that the electric field is equal to, basically goes as 1 over r squared and is proportional to the charge. Everything else is just a constant, isn't it? Yeah? Okay. So far, so good. You've seen all this before, right? What happens now if the charge is moving with respect to me? I'm now going to imagine a charge which is moving at a uniform velocity v. Okay? The charge is moving. If it's moving at a significant velocity, what would significant be? Can someone give me an example of a significant velocity where something interesting might happen? Come on, be bold.
Near the speed of light.
Near the speed of light. Obviously, it's got to be near the speed of light. Something interesting must be happening, mustn't it? Okay? So the charge is now moving, right? Now, one thing I already know about what is a moving charge, what else can we call a moving charge? Very fundamentally. A moving charge is also known as a current. It's a current. So a moving charge is a current. In the case of a pitted little proton, it's not a lot of current, but it is there, right? So there's a little current I moving along. And if it's a current, what do currents make, other than current buns? Sorry, sorry, I'll try not to do that too often. What does a current make? Makes a magnetic field. Okay? And in the case of a current going this way, in the direction of the proton, the magnetic field must be circuitous around the current, mustn't it? So there must be a magnetic field being generated, okay, called B. All right? And it must have some strength as a function of distance away from that charge. Again, we'll do that in detail a bit later. But it must be there, right? Okay? But let's go back to the electric field. What do I imagine might be important in terms of a calculation if I think of a charge moving and I compare that to the situation of a stationary charge? What will the pattern of the electric field lines look like, do you imagine? What transformation might I do if it's a relativistically moving object? What is the transformation you know about relativity? The Lorentz transformation. Okay. What do I know about rapidly moving objects when I do a Lorentz transformation? So you already know all this. What happens in the direction of motion? We have a Lorentz contraction. Okay. So all the lengths in the direction of motion of the charge must be contracted, mustn't they? Right. Now you can work this out more formally, but we expect that the electric field is compressed. Okay, so rather than being spread out uniformly in all directions, the electric field is now compressed to within some kind of angular separation. So it's like a disk of electric field. It spreads out a little bit forwards and back. Okay, and hopefully it shouldn't surprise you that the opening angle of that electric field, it goes as 1 over gamma. Okay, so when gamma is 1, the electric field spreads out uniformly over all angles, and as gamma goes up, the electric field becomes compressed. So very rapidly moving charge presents a very thin disk of electric field. Okay? So we're going to forget about the magnetic field. Let's look at the electric field. Now, notice that in the spherically symmetric case of a stationary charge, if I double the distance, the electric field goes down by a factor of 4, doesn't it? Okay? And it doesn't matter where I am looking at the charge. All right? Is that still the case in the situation of a moving charge? So it's moving at a constant velocity, okay? And the electric field has been compressed by the Lorentz transformation. I'm trying to slip on that water over there. God knows where it's come from. The electric field is compressed to a size 1 over gamma. Okay? The electric field, as it turns out, still falls as 1 over r squared, regardless of the direction I look at. Okay? Now you can show that formally, but we'll accept that in passing for now. This is just to whet your appetite. Okay? That's a very important statement, because we will see later that in order for radiation to occur, I have to have a component of the electric field that falls with another pattern. Okay? And we will see that in order for radiation to occur, right, the electric field, there must be a component of the electric field that falls as 1 over r, not as 1 over r squared. Okay? All right? So this is a very cursory description of what we're going to get into. A stationary charge does not emit radiation. Now you can see that, because you can see there is no, if the charge is stationary, nothing is changing with time at some distance far away. Yeah, that's straightforward to see, isn't it? And remember that we remarked that in order for radiation to be observed from in any situation, there has to be a varying electric field, and there has to be carrying energy. That's what we mean by electromagnetic radiation. Okay? And we'll formalize that concept later. Right? In a stationary charge situation, there is no such variation. Right? Another thing we can remark upon, and again we'll look at this again later, is that there is no magnetic field around a stationary charge. And remember that we already knew, didn't we, from some other considerations, that an electromagnetic wave, or photons, is the coupling together of two things. There's an electric field and a magnetic field. And in that stationary charge situation, there is no magnetic field, so therefore there can be no radiation. So there's two arguments that we've said there, why there is no radiation that's emanated from a stationary charge. Right? This second situation is a little bit more complicated, because now we have a uniformly moving charge. We do have a magnetic field, okay? And the magnetic field, as the charge goes by, does vary, doesn't it? And so does the electric field, right? So this is less obvious to see. So it's not immediately apparent that there is no radiation emitted from a uniformly moving charge. But what we can do is the following. We can say to ourselves, aha, I can always Lorentz transform myself into a frame where the charge is stationary. Okay? And when I do that, I get back to the situation where it looks like a stationary charge again, and therefore there's no radiation. And that's my starting trick. Again, we'll go through this again. That's my starting trick for relating together those two situations of a stationary and a moving charge. Right? So a moving charge, by that trick of being able to Lorentz transform backwards and forwards, a special relativity transformation, we can convince ourselves that a uniformly moving charge also does not radiate. All right? Okay? So those are 2 of 3 possible situations, aren't they? We have discounted the stationary charge, and we have discounted the uniformly moving charge. There is only one thing left. That situation where a Lorentz transformation does not apply in a simple way. And that must be the situation of acceleration. Okay? All right? So that's what I'm going to leave you with today. The statement is that in order for radiation to occur, there must be acceleration. Okay? Now we're going to come back to this picture later, but hopefully this will enthuse you about where we're going. Right? Here is our statement about the charge. Because what we're really saying about radiation, remember, this is a classical physics statement, but we are going to invoke relativity directly. Because we think what an acceleration is. You see, if there is a Lorentz transformation, we can, the uniformly moving object still looks uniformly moving wherever I'm looking, okay? But if I have an observer over here, okay, looking at that charge, and I accelerate the charge may move from one location to another. Let's draw a little dot there. But my knowledge that it is moved cannot be known by the observer until a certain time has elapsed. Yeah? It takes a certain amount of time for the knowledge that the charge has moved to get to the observer. Right? So before that time has elapsed, what does the observer know about the position of the charge? Well, the observer knows the electric field, doesn't he? She. Yeah? So clearly, at the time when the charge is accelerated, and for some time after that, the electric field near the observer must be what it was before. Right? Okay? So I imagine I move the charge. I do a very, very good acceleration, a little instantaneous jump, for argument's sake, which is the way in which we derive a great derivation of the Larmor formula. It's called Purcell's method. It's a Google search. Okay? We're going to come to that later. Right? So I bump the charge by a little bit, and clearly the electric field near to the charge moves with the charge, as long as I'm sufficiently close. Okay? But further away, the electric field is what it was before. So if I were to draw the field lines at some time in between, I count up the seconds between when the charge was moved and the time it takes for that information to have travelled to the observer, at somewhere in between, right, there must be a jump between the new electric field and the old electric field. Okay? There must be a jump in the electric field. Quite what's happening on those electric field lines is an interesting one, isn't it? We know that electric field lines must be continuous. We can't be adding or subtracting electric fields there, can we? Because if we were, there must be some charge there. We know there's not. Right? So there must be a jump in the electric field. Turns out that's not too bad. That's okay mathematically. Right? But we also know that little jump there must be moving outwards. And what speed is it moving outwards at? The speed of light, clearly, because that's the speed at which the information. And of course, that is our radiation. Okay? So that is the conceptual statement about the course. We will look at it in more detail, but the statement is that an accelerating charge emanates a kink in the electric field, and that kink travels away at the speed of light. And we will show that's consistent with all our other information about how electric fields travel. Okay? So for the proper lectures now, we're going to go into looking at the movement of electromagnetic waves, but we'll come back to this and we'll look at it in detail and we'll derive that formula. And you should start to think about the shape of the electric field around that moved charge. You can draw that for yourself and you'll figure out which way the photons are going. Okay? And that's everything you need to know about antennas. We'll do that later. Okay, that's it for today. Thank you very much. And we'll see you on Friday. Was that audible? Yeah, good. Was it interesting? Good. I want it to be interesting and audible. Maybe not both at the same time. Oh, hello. Thank you very much. I almost lost those. Thank you. Oh, hello, you next up. What course are you doing?
Optometry.
Optometry? Mm-hmm. As in for ophthalmology or?
As in for optometry.
Yeah, oh, okay. Right, I'll take my stuff away. I'm going to try not to lose any pens. I think that's it, yes. And my weight guides, God, I can't lose those.
second.